everybody. So today we are trying to discuss a little bit on HPE iLO. It's a BMC system. Let me just before introduce my partner in crimes, Alexandre Gazet and Fabien Perigot. So short outline. So iLO, integrated light out. So it's a BMC system. So it's really famous from HPE server. It's more famous for 10 years now. It's provide a lot of remote administration features. For example, you can check the power management, remote system console. You can mount some ISO, so some image you can mount and you can reboot the server to run on this ISO. And there is also a lot of monitoring indicators. This talk is focused on the version 4, so the latest version in middle of 2017. And this version is really present in the Gen 8 and Gen 9 HPE ProLiant. About the version of the firmware, it's a version 2.44 and 2.50. What it looks like in terms of hardware, it's a chip on the motherboard. It's a dedicated ARM processor. The firmware is stored on the NAND, on the flash. There is a dedicated RAM chip and also dedicated network interfaces. An interesting fact, iLO run when the power cord is plugged on the server. So you don't need to boot the system or the host should be up. If you just plug the power, the iLO runs. In terms of hardware privilege access, so there is, of course, some access for the screen, so you can deport the screen, so you can look the screen from the iLO. You can inject some keystroke for the keyboard. And a really interesting feature that we come back later, it's a PCI Express bus. It's directly connected on the PCI Express bus. In my case, for sure, I'm more than pen testers at a reverse engineer. So there is a lot of well-known pen test tricks for iLO. The first one is EPMI bypass with a cipher O. This one has been fixed. The other one is really interesting because it's by design, so you can retrieve the password hash just to request an authentication step. So just request to the iLO an authentication through IPMI, and you get the real hash, and then you can try to brute force and recover the password. So if you would like more information about that, just below there is some pointer in some URL when you can have some detail on that. If you look on internet, the big internet, there is more than 20,000 iLO exposed in internet. If you filter from iLO4, yes, there is more than 4,000 iLOs that expose directly on internet. But it's showdown, so some of them has been disappeared or not been connected yet. If you run your own scan, for example, so this scan has been run in September 2017. There is more than 3,000 interfaces. So there is a lot of version, and if you run the same scan, so the last month I ran the same scan, you can see there is some old version has been removed, but it's not really, not a lot of people try to keep up to date this version of the firmware on iLO. Just a simple screenshot about what it looks like when you try to connect on the web interfaces on iLO4. It's just a simple iLO pictures with a login and password.
So now let's talk about the reasons why we started this study. So as we just saw, the iLO is a kind of critical infrastructure. It provides remote management of your HP servers. We also frequently encountered it during pen test engagements. So it should normally only be exposed on the administration LAN, but as you can see, there were many iLO exposed on the internet, and in internal LAN, you usually can reach iLOs from the workstation LAN. Also, there are known weaknesses in the authentication protocol, and they are really too rarely monitored. So the objectives of the study was to assess the trust we can put in this technology, and for this we had to understand the product and more than the product, its internals. We also had to try to understand what was the exposed attack surface and what were the risks we faced using iLO on the network. About the results, so little spoiler, we found one critical vulnerability with a very high CVSS score. This vulnerability allows authentication bypass and remote code execution on the iLO. It has been fixed in iLO4 versions 2, 53, and 54. Using this vulnerability, we were able to fully compromise the server, so we were able to compromise the host from the iLO and also to backdoor the iLO firmware. To finish this introduction, a little timeline. So we did responsible disclosure. So the vulnerability was discovered in February last year. We reported it to HPE in the end of February through the Airbus cert. One day after, HPE acknowledged the report and told us that they forwarded to the iLO team. And then 3 months later, they released a new iLO version which silently fixed the vulnerability, so there were no advisory at all. And they didn't contact us. So a few months later, the Airbus cert tried to obtain a CV ID for this vulnerability. And then a few days later, HPE contacted the Airbus cert saying, well, there was some problems in the communication, and well, we will finally release a security bulletin. So, well, finally in August, they released the security bulletin about this vulnerability. Now, so let's talk about the technical aspects.
Yeah, about the study itself. Like often with embedded-like system, the main entry point is the update mechanism. That's where we can get a firmware and start to analyze them. So that's what we did for this study as well. You can, of course, grab the firmware from the main HPE website, obviously. There's this great website, pingtool.org, where lots of previous versions of this firmware are archived. So it's a good source of information if you want to go back in time to see when some code have changed, or of course to get the last version. When we started this study, like we presented before, it was mainly on versions iLO4 2.44 and 2.50. So we just grab one of these update packages. So, actually, that's one that is supposed to run on Windows. We start to unpack all the components. So if we unpack the main exe file, we found 4 files. 2 of them are of higher importance. The first one is flash_iLO4, which is a flashing tool that it means to run on the Windows system. It's x86 code. And the other one is the iLO _version.bin, which is the actual firmware. It's a binary blob, which is made of first, HP sign file header, which is some text header, which embed the signatures. And just after, there are 3 HP certificates concatenated. And after that, a binary blob, a large binary blob with the header HP image. So we will go to see that one. This HP image header is its size is 4B8. It doesn't have much information. There's a version, a GUID, but not much interesting. So we will skip this header and concentrate on the rest of the binary blob. If we go to the end of the file, to the end of this binary blob, we found a reversed header with the iLO4 marker just at the end. And just a few bytes before, an offset, a negative offset to another very important structures, which are the cryptographic parameter, which will be used to verify the signature of the image that are embedded within the HP image blob. So within this parameter, we found the modulus and the exponent of an RSA signature that will be verified by the bootloader. They will be verified later. Another very characteristic thing that we quickly found, 10,000 bytes from the end of the file, we quickly recognize some IRM code at the end of the blob. Actually, that's the bootstrap code that is used to load and verify the integrity and then load the appropriate image from the HPE image blob. So now we will go back to the beginning of this blob again. We will find many AMG header structures. Actually, we'll see there are 3 in this binary. At the beginning of this structure, we find again the iLO4 magic, version strings, and other useful information. All these sub-images are signed using the, and the signature can be verified using the cryptographic parameters that we've discovered before. Like I said, 3 images, userland, and 2 for kernel, main and recovery, we guess so. These images are possibly compressed. There's a flag that indicates you if it's compressed or not. It's an LZ-like algorithm that we found in the bootstrap code. We reversed it and we implemented in our tools to get it easier. So just a summary of this structure. Main fields of most important fields are the versions, of course, if it is compressed or not, and the compressed size, of course, and the load address. And there's, of course, a signature, which is important. So we did extract all of these sub-images. One of them was more interesting than the other. Once it was extracted, it was actually an ELF file. So far, the key takeaways for us is that we understand how the update package is made. We can extract images from the binary blob. All these sub-images are signed, and they're verified by the x36 code and by the bootloader code. And the main image is a 32 meg ELF file, and we will dig into it just now. So once we start analyzing this big ELF file, one can quickly see that there's lots of sections, actually a very large number of sections, a bit unusual. If we go to look at these sections, we quickly found some sections names that are really interesting, especially the limb integrity sections. There's many more sections. You can see there's text section, data section, etc. And at the end, we have 2 special sections that are boot table and secinfo section. Like I said, lib integrity sections was important. There's lots of strings within this binary firmware that leads us to the fact that this firmware actually runs over the Integrity Real-Time OS, that is a real-time OS developed by a society named GreenHills Softwares. There's lots of build paths that are embedded within the firmware, and we can guess that easily. So the ELF binary that we are looking at is actually an applicative image. So it's like a userland package that is made by HPE, built by HPE, and that runs on the Integrity Real-Time kernel OS. So, like I said previously, 2 sections from the main ELF files are critical to understand how this userland package will be loaded into memory. These are the secinfo and boot table sections. So we'll start by looking at the secinfo sections. It's actually a list of what we have called section info structures, linked list. Most important fields, of course, the name, and where it will be loaded in memory, where it can be found, within the ELF file, and the section size, and the rights which are associated with the section. So we can dump the section list. We found many of them, of course. Section offset is an offset within the main ELF file, and the rights can take up to 3 values, 1 for executable section, 9 for statically defined data, and C for uninitialized data. So we have this information, and now we will look at the boot table sections. It is way more complex, actually, but still it relies on the information it can grab from the secinfo sections. And the boot table section actually contains all the information that are needed to rebuild the virtual memory mapping of all the tasks that will be running in the integrity image. So at the beginning of this section, we have actually two very important pointers. The first one is task.conf, and the last one, list_core. We will start by looking at a list_core. It's actually a list of shared modules that can be loaded within many different tasks. There are actually 5 shared modules. The one that is dedicated to management of integrity and I guess communication with the server, the libc, some libs that will be responsible for event logging, etc. And then we will look at the structures that are pointed by the task.conf pointer. It's a list of task descriptor. We have named it task.info. Yeah, the type field seems to take only 2 values, one for the kernel task and 21 other RAS. Within these structures, there's a very important component that is the vmem space array. That is actually a pointer to an array of mem range descriptor, which is a mem range descriptor I used to fully describe the virtual memory space of the tasks. This structure is has many fields. The first one is present. It is set to 1 if the range is loaded from the content of the help file. And the right, so the next field is right. 5 for executable range, 7 for data, and again, there's no distinction between data, stack, or other kind of memory. And the idea is it's very important to understand how it works and to link all the elements together. It's actually a shifting index within the main elf file header. And the shift is equal to the number of modules or number of tasks. So when you are able to parse all this information, you can quickly rebuild all the virtual memory of a task. That's what we have here, just an extract of the virtual memory mapping for the web server tasks. So again, we will just to conclude this section. So far, we have an extensive understanding of the integrity applicative image format. We are now able to find how many tasks are running and how their virtual memory space is built. Something important, all the tasks have their main .text section loaded at 10,000. And what we have done is we have automatized this process of task extraction, and we have scripts to automatically build the appropriate IDB with all the components properly loaded into the IDB. And yeah, the script will be released next week as soon as we come back. So now we have a clear view of the userland applicative image. We will, before we start looking really at this userland task, we will go and look at the kernel, the integrity kernel. So let's discuss about the internals of the kernel. So we had absolutely no information other than what is displayed on their main website, which is very scarce information. We had no technical information available to us. So what we know is only that what they call apps are meant to run into what they call protected virtual address spaces. Okay. So all the rest we did was to reverse engineer the kernel. Just to give you a few key elements about kernel, it's kind of microkernel built upon a small set of core modules. There's a small list somewhere within the image, kernel image. Of what we have called boot mode structures. Each of these structures has a constructor, destructor. Maybe these modules can be loaded or unloaded, but I guess some it would be impossible. Each module has a name, of course, and yeah, something very important, a pointer to a list of dependencies. If we dump these components, we see that the resource manager is the main module, and most of the other, actually all the other modules will depend upon it. We have interesting components like the one handling network communication and things like that. But yeah, what is key here is that all the modules depends upon the resource manager, and it will be key to understand what we did after. So it seems to work like you instantiate some objects and you create some resources, and that can be shared amongst the tasks that are running in the userland, and the kernel is handling all this stuff for you. So what we have is a typical code that we can find within the kernel that instantiates an object. It will actually set up and send a request, which will be made of a verb, which is in this case reglink, the name of the object, in this case loader connections, and a password, which seems to be fixed everywhere within this image, both userland and kernelland, which is a bank system password. There are few supported verbs, which are procure, delete, register, reglink, and procure, delete. Yeah, so far that's it. There's also an equivalent of the secinfo sections. It's some kind of symbol tables that are useful to give proper names to some memory area where you have mapped within your kernel database. Another thing that will be really important, that we found, is that very early in the early initialization phase, we found some code that is responsible to parse some kind of memory descriptor regions. Near that code, we found some debug message that we know that this code is related to a BSP, so a board support package. That's a place where you describe how the hardware element, where it can be found, etc., memory address. And yeah, what is really important is that these memory descriptors will be registered as resources with the code you see below the slides. So we will dump all these memory descriptor. We name these memory regions. We have the lower address and the high address. And it is each of this object is given a name, and it will be a linked list also, double linked list. So once you dump all these memory descriptor objects, we have their name and where they will be mapped into memory. And later, if a userland task wants to require one of these objects, it will simply ask the kernel to instantiate it for it, using the name, for example, msram_asm. So that's it for the internals. And now let's get back to the study of the iLO itself.
Okay, so about the attack surface of the iLO. So there are, in fact, 2 point of views regarding the attack surface. The first one being how can we reach the iLO from the host operating system? So HPE provides, in fact, access to the iLO when you run your operating system on the main CPU. And the iLO is seen, in fact, as a PCI device. And, for example, for Linux, a driver is already provided by the Linux kernel. And on the iLO side, this communication between the host and the iLO is provided by a task called chief, which stands for channel interface. This task has various command handlers. This task also gives access to the Redfish API from the host server. So there's, in fact, an API to configure the iLO server. And also the chief can pass some commands to other tasks running on the iLO, such as the embedded media task, which allows you to mount an ISO file on the host. How does the communication channel works? In fact, commands are passed through shared memory. The Linux driver implements 8 to 24 channels in the device shared memory, and commands are sent in a FIFO. So a command, in fact, follows the following structure. So it has a size, a command ID, a destination ID, which tells which service should be joined on the iLO part, and some data as arguments. One important thing to note is that the iLO access from the host is privileged, which means that you don't need to authenticate to access these iLO functions. So, for example, from the host, you are able to add new users or new administrators on the iLO without any authentication. You're able to access the Redfish API, which allows you to fully configure the iLO. And well, one example of commands which can be sent from the host to the iLO is the one to read the EEPROM, which stores the default settings. So each iLO comes provisioned with an administrator default password, which is different from each iLO, and it's stored in a specific EEPROM. So while you can just send the command ID 70 to the iLO and just get, as a result, a dump of the EEPROM containing the default administrator password.
Related for the network point of view, so there is there is some services that expose. So there is a SSH, there is a web server that we already introduced. On this web server, there is a RESTful API. There is also a dedicated server that Fabian discussed just before about the fact you can mount an ISO from the iLO in order to boot on this ISO. There is IPMI, of course, SNMP, and UPnP. So now let's look on the web server. So if you are authenticated on the web server, what it looks like is this one. So you can manage easily the hardware. You have a lot of indicators about the hardware. You can run the Java applet, which allow you to reach the console on the host. So from this screen, you can manipulate directly like a console on the host. The web server provides so a shiny web interface with some indicators, not lots of them, an XML API, Redfish API, and that I said the Java applet to reach the remote console. The really good point, it's all these pages from the web servers should be you should be authenticated. So you could not reach them if you are not a valid credential to log on the web server. The bad one, it's you have one endpoint named XML data you can access without any authentication. And from this endpoint, what you can recover, for example, so you can recover, of course, the version of iLO that you use. So iLO4 in this case. You have also some information related of the server itself. So it's a ProLiant G8 in these cases. The version of the firmware it's running 2.55, and so on. Another good information about this XML data endpoint, you can recover the external and internal IP address. So what I said for external and internal, so you have the IP address from the iLO, but in some cases you can recover also the IP address from the real host. So you can expose the iLO, but you have no ID which is the IP address of the host behind. And in this case, you can sometimes recover. It's only used for the iLO4, for example, iLO4 and iLO5, not before. But you can recover the real IP address on the host. So that's interesting to have this information for the next step. But yeah, let's see. And not least, you get also a free advanced license. You just recover this one and you get a free license. So yeah, if you don't want to bypass, you can easily get a license for free.
One last thing, after authentication, there's a hidden debug page which can be accessed. So, well, this is kind of a teasing for later, but it provides various internal technical information, such as, for example, information about various PCI register values. So now we will take a look at the web server architecture. So web servers has 4 concurrent threads running in parallel. Each thread handles specific connections, which means that you can only have 4 concurrent connections to the web server. And it supports, of course, HTTP and HTTPS. How is a new connection handled? So each request, each HTTP request is passed line by the web server with various string compare, str, and scanf calls. So, well, doing parsing in C is hard. So, what could go wrong here? Well, so using scanf is not so easy. Here we can see that the parsing of the main method and URL is done with the correct size specifiers for the strings, so it's okay. On this one, the authorization header, well, seems okay. The content length is just an in parsing, it seems okay, but well, for the connection header, you can see that it's a %s without any size specifiers, so well, it seems not so good. Well, this is the high-level view of the web server parsing. So well, for each header, there's a kind of switch case, and we can see that for the connection header, it just retrieves the value of the header and copies it in the connection field of an HTTPS connection. Well, so a quick remember on how this scanf function works. So you can parse a string by specifying a specific format, and well, when you don't provide a size for the %s specifier, well, you can just overflow a fixed size buffer. In our case, the buffer is 16 bytes long, so well, if you provide a string longer than 16, you overflow the buffer. Well, in our case, so the argument passed to the function here is R7 plus C. R7 points to an HTTPS connection object, and so at offset C of this object, there's a fixed size connection buffer of 16 bytes. And what's interesting is that, well, some bytes after this this buffer, there's also a local connection field. So let's see what it is. Well, a quick remember, we said earlier that the host system can talk to the iLO through the shared memory system. The host can access the redfish memory from the host, and no authentication is required. So, while the web server uses this Boolean local connection to remember if the request comes from the local host or from the network. So, well, so the redfish API will allow unauthenticated access when this Boolean is not set to 0. So what could happen if we overflow the buffer to change the value of this local connection buffer? So this will be a first demo. So, well, we can see we are trying here to access the redfish API, so we don't provide any authentication, so we are, we got 401 code unauthenticated. We prepare a value of 29 A's, and then we will craft a specific connection header here with this value. And then, well, magic happens. And there we authorize and we can access the redfish API. So, well, it's a quick authentication bypass, and it's, well, very stable. So the key takeaways for this part. So we have a pre-authentication buffer overflow in the web server HTTP headers parsing. This is, in fact, the vulnerability we reported to HPE in last year. So the vulnerability can be exploited to bypass authentication and access the redfish API. So, well, from there you can add a new administrator account, you can access the remote console, you can even restart the server on an ISO you provide through the network. So, well, it's kind of complete takeover of the server, but we can go deeper. So we will now try to transform this simple authentication bypass into a real code execution on the iLO. Fortunately, the objects created by the web server have their vtable pointer in the end of the object, which means that if we overflow enough, we can change the value of the vtable pointer. And, well, there's no randomization and no execution prevention. So, well, it makes the life easier when we are in a remote exploitation case. And each web server thread has a working buffer, its own working buffer at a fixed address in the virtual memory. So here's the virtual memory layout of the web server. And in the .data section, we have 4 huge buffers used by each web server thread to, in fact, store each line of the HTTP request it passes. So it means that these working buffers can be populated by control data by providing arbitrary headers. So what we will do is, in fact, write a shellcode in this working buffer, then write a fake vtable pointing on this shellcode, and then just trigger the overflow to point on this fake vtable, and then we hope that there will be a call somewhere in the code calling our shellcode. And, well, then now that we can execute arbitrary shellcode on the iLO, well, what can we do more than the simple authentication bypass? Well, for example, we can try to read the password file on the iLO file system. Fortunately, passwords are all stored in clear text on iLO, so we can read the file and send the result back in the HTTPS socket. The demonstration. So we run the exploit on the iLO server. We specify the version. And then, well, we can retrieve first the default administrator password and then the password for another account which has been configured on the iLO. So for now, we are able to turn the buffer overflow into a reliable code execution on the iLO. We can now execute an arbitrary shellcode on in the web server task contest. And but while we want to go deeper, we think that the iLO could access the host main physical memory, and that there may be a way to compromise the host operating system. Well, so an interesting task to study for this was the chief task. If you remember, the chief task was responsible for communication between the iLO and the host. And during the reversing of this task, we saw mentions of WHEA records parsing. So WHEA stands for Windows Hardware Error Architecture, which is well, something developed by Microsoft to provide error detection and handling by hardware. And if you look at these strings, we can see that for parsing the WHEA records, it first reads the SMBIOS entry to 29, and we also see reference to Ostram, so we can think we are on the good way. So, well, first we took a look at the type 22029 SMBIOS entry. Well, it's OEM defined, so it's defined by HPE. We dumped it from the Linux host running on the server, and well, it looks like there are a few different structures composed of the first a tag, then something which looks like a 64 bits pointer, and then well, some flags. So what we try to do is retrieve these pointers and have a look in the physical memory to see if well, it matches something interesting. So if we have a look at one of these pointers, while we retrieve the same kind of tag and some information related to HPE, so while we think we are on the good way, and that this pointer should be pointers to physical memory on the main memory. So if we have a look on the chief binary and how it parses the WHEA records, we first see that they retrieve this SMBIOS entry, they find a specific tag, and if the tag is found, they will retrieve the pointer, pass it to a specific function, and then perform some memcopy to fill their WHEA header structure. So, well, what we can think is that this function allows to access some part of physical memory on the host. So we will dig into this function's code. So it's not very huge. In fact, it just takes a 64 bits pointer. It truncates it to a 16 megabytes boundary. So by shifting it by 24, it sets a specific flag, and it writes it in address 1F02064, and then returns address 600000 plus the low part of the pointer which was discarded before. So well, now we just have two questions. First, what is mapped at this address where we rewrite this magic value, and then what is mapped at the address returned by the function. Earlier, Alex told us about memory regions. So these are description of ranges of iLO physical memory. They can be mapped in a userland task virtual memory by asking the kernel using the request resource API. And each task, each userland task has a a list of memory region it can map in its virtual memory by calling a function memmap. So, well, we will try to parse these various entries and have a look. So for the chief task, it has the following memory region it can map in its address space. And we can find the two ranges of interest for us. So we now can have our virtual physical memory mapping between the virtual address space of the user land and the memory regions. Finally, one more thing. We told you earlier about the debug HTML page giving information about PCI register. So we reversed the handler for this page to see where the iLO was reading to get the information about the PCI register. And we found that in the range of the 1F000 memory range, there were various PCI register mapped. So we didn't find the exact value we were looking for, but we can imagine that this is also a PCI register. So now that we've reversed the chief to see how it accesses the host memory, what we want to do is trying to re-implement this technique in the web server task through the shellcode and see if we can read host memory. So what we have to do is just take a host physical memory address, we shift it by 24, we add the magic flag, we write it to the PCI register, and we try to read the memory region. And well, after testing this, we saw that in fact we can access almost any memory address in the host physical memory and have both read and write access to it. So, well, using this very strong primitive of read and write in the physical memory, we can try to pawn the host. So the host, in our case, runs an up-to-date Ubuntu Linux. So, well, the plan will be first to read the memory to try to dump the Linux kernel address space, then do some parsing to find some interesting offsets, replace some unused function in the kernel with our shellcode. Well, it's a bit dirty, but it works. And then finally, hijack the syscall table to redirect execution to our shellcode. So what we will do is simply hijack the sysread system call, which is very often called on the server to redirect to the shellcode. So here on the right, you can see the Ubuntu running on the host server, and on the left is the attacker machine. So as you can see on the server, there's nothing weird listening on a TCP port. If we try to connect from the machine, we can't. So first, we will, as I said, leak some memory to retrieve the Linux kernel address space, so that we can parse it to retrieve, for example, the syscall table and the function we need in our shellcode. So, well, now it has been dumped, we will try to retrieve interesting offsets. So we found the syscall table, the sysread, the call user mod helper, which helps running code in userland from the Linux kernel, and, well, an unused function related to serial which we can overwrite with our shellcode. So then we will overwrite this function with our shellcode. So this is, well, simple shellcode. We will spawn a netcat listening on a specific port. And finally, we will patch the syscall table sysread entry to point to our shellcode. And, well, now if we have a look on the server, there's something listening on the port, and, well, we can connect to it and we route. So can we do more? Now that we have fully compromised the host operating system, what we would like to do is to remain persistent across reboots and maybe across reinstallation without modifying, in fact, the file system on the host. So let's investigate this.
Yeah, so just a few words to conclude this study. Like Fabien said, with a point of view of an attacker that wants to stay in the place once he has compromised the iLO server and possibly compromise the host and all the network behind it. We want to survive a possible OS reinstallation and possible also iLO firmware updates. So at the beginning of the talk, we've seen that all the updates are signed. There's actually multiple signatures on different components of the what we could say update packages, and all these signatures are verified at boot time. So what can we do to gain some kind of persistence? Firmware updates can be performed either using the iLO web interface directly. You upload your firmware and it will do it for you, or you can do it from the host operating system, running, for example, the Windows package that we saw at the very beginning of this talk. When we looked at the update mechanism, there were two really important points. First, downgrading is possible. So if you gain access to a system, you can possibly go back to a previous version that is more variable, or maybe a version that presents a vulnerability that you want to exploit. We found that the signatures are correctly checked. Nothing really interesting to say about it. Still, the fact is, if we gain remote code execution on the iLO, it means we can bypass some of the signatures that are made, and we can directly write on the firmware, on the flash chip that contains the firmware. According to HP, all the components are checked at boot time. It's true, actually, but the fact is that the bootloader that does the job, and nobody verifies the bootloader signatures. So if we want to gain persistence quickly, we can patch the bootloader signature checks of the integrity kernel, then patch kernel signature of the userland parts. We can possibly, if we want to have something much more complex and powerful, inject a message payload that will hijack and re-inject the backdoor we have implemented in the firmware if the firmware is updated. We rebuild the correct image, and we will directly flash it on the chip. And all of this is possible on version 4. HP introduced what iLO4 at midsummer 2017, and they introduced what they call a feature they call silicon root of trust, which is, of course, some kind of secure boot. So just to conclude our talks, we try to propose some documentation about the internals of the integrity image and kernel internals. iLO4 at least expose a huge attack surface. There's many things exposed, SSH, web server, etc. Some of these features are still weak by design, like the well-known IPME v2 authentication schemes. We discovered one critical vulnerability that has been reported to the vendor, fixed, like we said at the beginning. An unpatched server means a trivial remote authentication bypass, so mostly full compromise. We have also proposed a full compromise of both the iLO system and the host system using the remote code execution features that we've proposed using the DMA-based exploitation technique using the memory region objects. Like I said just before, there's no hardware root of trust that opens door to compromised firmware and highly stealth and persistent attacker. And the conclusion of that is that remote administration service like this should always be isolated from, of course, internet and even of dedicated VLAN. Yeah. So yes, thank you for all your attentions. We will publish the slide and the scripts very soon, next week. If you have questions or want to contact us, there are our email here. Thank you.
Thank you.
Questions?
Thank you. Thank you.